Hey everyone, so today we're going to be reviewing the Simple Harmonic Motion content for the AP Physics 1 exam. So Simple Harmonic Motion doesn't account for a big percentage of the national exam, but it's still a nice refresher in terms of pretty much every unit, right? Like forces, energy, and a bunch of stuff. So Simple Harmonic Motion, so what exactly is it? So it's whenever you have what is a repetitive motion, and it's going to occur because of a restoring force, which is always trying to push the system back to its equilibrium position. So in these examples, you'll see conservation of energy, negligible friction, and stuff like that. So a couple key vocab terms that you're going to need to know for this unit is period. So that's the time it takes to complete one full cycle and pretty much return back to its starting position after it oscillates. Then you have frequency, and that's sort of like the inverse of that. That's just the number of cycles per second. So you can see the equation of T equals 1 over frequency. And then you have amplitude, right? That's just the maximum position from the equilibrium position that your block or your pendulum reaches when it oscillates. So let's first look at a pendulum. So the equation for a pendulum is 2 pi times square root of length of the pendulum over the gravitational constant. So something to know about the equation is that it is independent of the amplitude, right? So if you zoom in on this ball, we can see that what is the restoring force is the tangential component of Fg. And this is the force right here. You can see that mg sine theta is what gives you that tangential force. And that's going to push that pendulum back towards its equilibrium position. It's not going to stop there. Because there's conservation of energy, right? So it's going to go from its maximum amplitude position to its maximum negative amplitude position. And as you increase that angle of release, the initial release position, that's always going to affect the mg sine theta for the tangential component of Fg, and therefore your restoring force is also going to change. Next, let's talk about the horizontal mass spring system. So this is frictionless. So the equation for a spring is just 2 pi times square root of mass over the spring constant. It is also independent of the amplitude. So here's a nice diagram. It shows that initially your block is at rest in what is called equilibrium. All right, but let's say we stretch it out. So now it has spring potential energy. So at this position, the acceleration is going to be negative max, the force is going to be maximum, and your velocity is going to be 0. So this isn't really representative of you pulling it and stretching it to that position, but this is just when it's oscillating. When it reaches that position, these are the standard values. So if it goes from position 2 to 3, when it's oscillating, when it reaches the equilibrium position, your force on it is going to be 0, and therefore your acceleration is also 0. And that's also when you reach your maximum velocity. When it reaches the other side, that negative amplitude, it's very similar to position 2, where the force is the maximum, but the acceleration is also maximum, except now it's in the positive direction because you're trying to go to the right side, right, to bring that mass on the spring back towards that equilibrium position, and then your velocity is 0. All right, so here is a table summary of just general simple harmonic motions. And on this side, we have some motion graphs. So these motion graphs are just a way to represent motion, and we can see that it's representative of this spring mass system that is oscillating. So if we look at it, position 2 represents that maximum position away. You see here, position 2, maximum distance away from that equilibrium position, and therefore at the maximum amplitude in the positive direction. And then as it goes towards that equilibrium position, you're going to hit x equals 0, which is representative of position 3. Then it goes to its negative at 4 and comes back. Now for velocity, you can see a very similar trend. So for the maximum position at 2, you're going to have 0 velocity, right? Because acceleration is max, the force is max. But when it reaches the endpoints of equilibrium position, so position 3, that is when we talked about how the velocity is going to be maximum, right? So you see how the velocity for position 3 is maximum, whereas the other positions, the velocity is 0. Now for acceleration, very similar trends. So when it reaches its equilibrium position, there is no acceleration. But when it reaches its endpoints, it has that maximum acceleration. So that's just a quick content review of Simple Harmonic Motion. If you guys learned something, make sure you subscribe, and thank you for watching.